Good morning, class. Today's lesson is 2.6 about the infinite set. We've talked about a variety of ways to look at sets. We've looked at short lists of numbers, things where we can count the cardinality pretty easy on one hand. I think our biggest set was about 10. Today we're looking at infinite sets. We're going to go out and beyond. So let's review a little bit here. First off, to define infinite sets, we have to be able to set up a proper subset of a set, and let's review what that means. So you can see here in this example here, 1, 2, and 3 are a proper subset of this series because there's the 1, there's the 2, there's the 3, they're all part of it. The next example we have here, A is a proper subset of ABC because again, A is right here, happy, happy. Down below here, the third one, XYZ, is not a proper subset of XYZ because they are the same terms. Proper subset A is a proper subset of B if and only if all the elements of set A are elements of set B and set A is not equal to set B. Let's move it to the next stage here. We've got infinite sets. A set that can be placed in a one-to-one correspondence with a proper subset of itself. So the counting numbers, for example, 1, 2, 3, 4, 5, n, So if we kept going, the dots continued. How could we make this work? Well, in this example, we're just going to chop off this first one. And now we start 2, 3, 4, 5, 6, n plus 1. That works. We are going to be able to show that these numbers are a proper subset of the counting numbers. Keep that in the back of your mind because we're about to get going. Here's example 1. Show that the set of even counting numbers is an infinite set. That means that we've got this ellipse at the end, and this will work all the way to infinity. Well, for this example, what we're going to do is we're going to chop this first number off, shift everything down by 1, and now we've got 4. And so what we're looking for is correspondence between 2, 4, 4, 6, 6, 8. Is there a relationship? Absolutely. The relationship is, since we're moving up to n, and we add 2, we're going to get the next number in the series. So if we've got 10 here, that means we're going to have 12 down here, etc., etc., etc. So this is a one-to-one correspondence. If we get that to show up, bada boom, bada bing, we got us an infinite set. That's awesome. Moving on. Moving on to example 2, show that the set of multiples of 5 is an infinite set. Same kind of concept here. We've got our series, and we get this n value out here way down the road. What we do is chop that first one off, shift everything over by 1, and now we show, is there correspondence between these guys? Guess what? There is. Since we have 5n as our growth value, we're moving up by 5n every time. We can get to the next number by adding a 5 to that. So this is an infinite set. Again, we're defining infinite sets. Not all sets are infinite sets, but we are defining what exactly is an infinite set. Okay, moving on. There we go. Moving on to countable sets. A set is countable if it is finite or if it can be placed in a one-to-one correspondence with a set of counting numbers. So here we've got a cardinality of 3 when A is ABC. Down below here, we need to figure out what is the cardinality, and we can figure this out actually because it's a figure outable thing, especially when we have a finite set. It's this thing here, and this little weird, it looks like a backwards Yankee New York thing. I don't know. We actually have a name for that doohickey, and it is a, let's see if it pops up here. Oh, there it is. It's alpha null. Alpha null. So when we see a cardinality and we're looking for the number here of one of these finite sets that we've been able to define, we can write then that cardinality as alpha null. Say it with me. Alpha null. Alpha null. Alpha null. All right, moving on to example 3. I think this is the last one for today. Show that the set of odd counting numbers has cardinality alpha null. Well, we've got our counting numbers here, 1, 2, 3, 4, 5. The odd counting numbers are going to be value that we can find. So we can find the odd numbers by saying 2n minus 1 when we're talking about these counting numbers. So if I go with the first one here, using this equation, 2 times 1 is 2, minus 1 is 1. You go to the next number here, 2 times 2 is 4, minus 1 is 3, etc., etc. 3 times 2 is 6, minus 1 is 5. So this is the relationship here that we have. So since there's a one-to-one correspondence, the cardinality of set O, this is called set O, that's where this O comes from, so odd, going odd here, set O, is alpha null. Whoa, that's awesome. All right, that's pretty much it. I mean, if you want to read through a couple more examples, you're welcome to do so, but the homework is a one-pager. It's only a handful, but in order to get full credit, you will need to do these things. Be sure you write out the original set. So you'll see that you've got the original set there listed in the homework. Write it out. Below it, write out the proper subset. Make sure that you're finding some way that they correspond. How do they correspond to each other? You're going to probably want to write about this. So verbalize, write. Tell me what's going on. And then lastly, show the pairing of the general terms in that set. So make sure you're showing like arrows work. So if you just do like a, this goes with this goes with this, sort of like the examples in the text, that's okay. But please do show that you understand what's going on here in your homework. And that is it for today's assignment. Have a good one.